Welcome back. This is EasySpin Academy 2020, and this is session 16 on day 3. In this session, we're going to look at the interface between EasySpin and ORCA, and we're also going to look at EasySpin's capabilities to simulate SQUID magnetometry data. First, let's look at the ORCA interface. EasySpin has a function to import ORCA calculation results, ORCA to EasySpin. Now, ORCA is a quantum chemistry program that allows one to calculate EPR parameters given a molecular structure. And how ORCA works, for those who are not familiar with it, is that you provide an input file like this here, where you initially specify the level of theory you want to apply. This specifies density functional theory. You give the density functional and the basis set. And then you specify the XYZ coordinates for a molecule. In this case, I've just added an oxygen, O, at position 0, 0, 0 in space, and a hydrogen at position 0, 0, 1.1. So basically, I've made an OH molecule. The overall charge of this molecule is 0, and it is a doublet spin. So it's an hydroxyl radical. Now what ORCA does, it solves the molecular orbitals for this molecule, and it also can calculate EPR parameters. In order to do that, you have to add a EPR NMR section to the input file called EPR NMR, and tell G-tensor1, the one just indicating that it should calculate the G-tensor. And then there's a nuclei section where you specify they should calculate for all protons the isotropic, dipolar, and orbital hyperfine contributions. Now, if you run this, you will get an output file that is very long, contains a lot of results about spin orbitals and populations and so on. And at some point further down, you will see a section about the electronic G-tensor, where it actually plots the full 3x3 matrix, but it also then gives the principal values, which are given here. In this case, 2.002, 2.006, and 2.077 for this hydroxyl radical. It also calculated the hyperfine parameters, in this case for one proton, that we've got. And so the raw hyperfine matrix here is also given as a 3x3 matrix in megahertz, which is consistent with EasySpin. And then, of course, also the eigenvalues if you want to see them. And you can see that it's -10, -116, -140 megahertz. So very large and very anisotropic. Okay. Now what you can do with EasySpin is you can load this output file, and I've created it. It is included in the distribution zip file that you received in the workshop. You could load this output file into EasySpin. And actually what EasySpin does, it does not read the output text file from ORCA, but it reads in a separate file that's a binary, and it's much smaller. It's called the prop file. And so every ORCA calculation generates this prop file. Don't throw them away. They're useful if you want to interface this with EasySpin. So we're going to include this hydroxyl_GA and load that in, hydroxyl_GA. You have to make sure you are in the right folder, and the current folder in MATLAB is shown here in this top toolbar here, just below the ribbon. And what ORCA to EasySpin reads this file in, and then puts all the information about the paramagnetic molecule into a spin system structure. Let's say clear CLC, and let's run this now. If you look in the workspace, now we do have a spin system structure that got generated, and we can look at it by just typing it in the command window. It has a variety of fields. It has XYZ coordinates. So sys.xyz actually contains the positions of those two atoms that were defined. It also contains the atomic numbers for the atoms, which are 8 and 1. 8 is for the oxygen and 1 for the hydrogen. But now importantly, it includes the calculated G-tensor, the G-frame, so the orientation of the G-tensor. It shows which nucleus it is, and the nucleus index that refers back to these atoms list, the hyperfine coupling tensor, and the orientation of the hyperfine coupling tensor. So this is all you need to actually simulate an EPR spectrum from these data. And also it would allow you to plot the geometry of the molecule because you know the positions and the atom numbers of the various atoms. Okay, so all as you can see, cis.nux has a hydrogen in there, which would include both the proton and the deuteron. But typically we only see a proton data. So let's modify this and just limit ourselves to a proton. We need to add a line broadening. LWPP is, let's say, 0.2 millitesla as usual. Specifying an experiment. Microwave frequency is 9.5. Let's go to X-band. And let's look at the output transitions separately. So output equals separate. And we can call pepper, cis, exp, opt. And let's run this. Let's see what happens. It plotted the spectrum. And voila, here it is. You've got 3 transitions, or actually 4. We see a red one, an orange one, a blue one, and a purple one, showing fairly large splittings. And if you set the opt output to summed instead of separate, and you run it, it will show you the overall spectrum, adding up all the subtransitions. So it only takes a few lines to import ORCA calculation results into EasySpin and quickly simulate the EPR spectrum. You don't have to deal with copy pasting the tensors or messing with the Euler angles. It's all taken care of automatically. So this is the ORCA interface. The next topic is magnetometry. So some people among you will probably have done SQUID magnetometry, and maybe for some of them this is your main measurement technique. EasySpin's function for magnetometry is called Curie. There's actually an interesting story behind that. Curie is kind of a pun on the name Curie, of course, but the idea of incorporating magnetometry into EasySpin came during a visit to Manchester while eating at one of those fantastic Indian restaurants there. So Curie now has capabilities to calculate a variety of magnetic quantities, such as the magnetic moment and the susceptibility. And the reason it is in EasySpin is actually because the underlying theory also utilizes spin Hamiltonians. And basically all that infrastructure already existed in EasySpin, so it was very easy to add on the magnetometry calculations. So let's do a simple calculation. We're gonna clear everything up first. Let's define a spin system, a spin 1/2 with a G value of 2. Now let's define a magnetic field. Let's say we sit at 5 Tesla, so 5,000 millitesla. And let's do a temperature sweep. Let's say we start at 2 Kelvin, then do increments of half Kelvin at the time until we hit 100 Kelvin. So this is also a very convenient syntax for those who are not familiar with it yet. It's a double colon syntax. It generates a kind of linear range array with the start value at the beginning, the increment in the middle, and the end value at the end. So now we define the experiment we're going to do. We specify the field to be B and the temperature, x plus temperature equal to T. I've just defined these 2 separate variables because I'm going to reuse them later in a different context. So all you need to do is the same call type you do for all other EasySpin functions. You name the function, you put in your sample information and your experiment information. Press Control Enter. And there you go. We've had no outputs requested, so Curie just plots a variety of quantities. Since we gave a temperature list and only one magnetic field, it actually calculated a temperature dependence. Right? And you can see 4 quantities that are being plotted. Maybe start on the top one here. That is the magnetic moment in units of Bohr magnetons. Kind of goes all the way up to almost 1 at 2 Kelvin, and it drops as you increase the temperature. Then there's also the molar magnetic moment along the z-axis, which has units of joules per Tesla per mole, and that goes from 5 down and decays as well. On the bottom, we have the magnetic susceptibility, which is kind of the derivative of the above quantities. And the molar magnetic susceptibility is shown here in the bottom left in cubic meter per mole, and you can see it rises and goes through a maximum and then starts decaying. And another quantity that's plotted quite often is the product of the susceptibility times the temperature, chi T, in units of Kelvin cubic meters per mole. And that keeps rising and then goes flat as the temperature increases. These are just a selection of the quantities that Curie can calculate. Now, as you see, all these units here are in cubic meters and moles and kelvins and joules. These are SI units. Now, the magnetochemistry community still uses the old CGS system quite a bit. And in order to accommodate that, Curie has an option where you say opt.units, and you can switch now to the CGS system. And the CGS system uses Gauss and centimeters and ERC and these kind of older units quite extensively. Okay, and now if you run Curie again, it basically gives you the output in CGS units. And you can see you have the magnetic moment in ERC per Gauss per mole and chi T in units of Kelvin cubic centimeters per mole and so on. And some of these numerical values are a little more amendable to use. If you go back to the SI system, you see, while for the CGS system, these are on the order of 0 to 1. In the SI system, they are 10 to the negative 6. So that is one reason why CGS units are used quite a bit in magnetochemistry. Okay, what we can do now, for example, we can compare this temperature dependence to of the molar magnetic susceptibility, this here, to the Curie law. So let's go switch back to SI units and now request Curie to just return us the molar susceptibility. So opt.output equals chi mole. So Curie can output so many different quantities that there is a choice. You can configure which one you actually want. In this case, we just want this molar susceptibility, and so the output is going to be chi mole. And maybe you should briefly show the documentation here. There is a user guide on SQUID magnetometry, and then there is the reference for the Curie function. If you look at the Curie function reference page, in the options, input options, you can see all the various quantities that Curie can calculate. Single center and molar, magnetic moments, and susceptibilities, basically. Okay, going back to this chi mole, this is how we calculate chi mole using the Curie function, which uses the spin Hamiltonian matrix and basically does an exact calculation. We can also write out the Curie law. I'm going to copy paste that as I prepared this. The Curie law, of course, depends on S times S plus 1 and G squared and on the temperature. And we can now plot these two results together. We could, let's see, we can now plot them as a function of temperature, T comma chi mole. This is the Curie calculated exact susceptibility, and T comma chi mole Curie, that is the Curie law. If you look at that, you can see in blue the exact calculation and in red the Curie law. You can see that the Curie law works well for higher temperatures, but it starts deviating quite a bit from the actual dependence at low temperatures. So this is how you can calculate simple things with Curie. One important thing that I want to remind everybody here in this context is exchange couplings. In magnetometry, often you look at exchange coupled systems, and exchange couplings in EasySpin are specified by sys.j. Now, there is a series of different conventions out there what this J actually means in terms of the spin Hamiltonian. So for example, it could mean plus J times S1 times S2. It could mean H equals minus J times S1 plus S2, or it could be minus 2 times J times S1 plus S2. So depending on the convention, of course, for a given J, you will get a different Hamiltonian. So the first one is used by EasySpin, but the third one is also very common. So whenever you pick a J value from literature, make sure to understand for which form of the exchange Hamiltonian this J value is for. Let's make an example here. 2 coupled spins. We're going to start out clean again. We don't need this here. And specify 2 coupled spins 1/2 for simplicity, 1/2, 1/2. Let's have both of them have G factors of 2. And now let's define a J. Let's say the J is 30, and we found this in the literature, and the value is in units of inverse centimeters, and it's for the Hamiltonian defined as minus 2 times J times S1 times S2. Okay, now we need to convert this to megahertz, because EasySpin takes megahertz, and then we have to take care of this -2 factor. So the first conversion is very simple. So we take J, it's in inverse centimeters, we multiply it by 100, we get inverse meters. We multiply it by the speed of light to convert it to hertz. And then we divide it by 1,000,000, so 10 to the 6, to convert it to megahertz. So this is the conversion from inverse centimeters to megahertz. Okay, and so that is the unit conversion. And now we just set sys.j equals to negative 2 times this calculated J. Because that's what the literature said it was down here, right? And EasySpin's convention is plus J. So sys.j, let's write that here, sys.j here equals -2j from the other form of the Hamiltonian. So be mindful of this fact that there are multiple conventions out there. So let's set a field range now, just for a change. Again, a linear space from like 0 to 8 Tesla. So I'm making an array that starts at 0 and ends at 8 with 50 points, and multiplying it by 1000 to convert it to millitesla. And that sets a temperature of helium, like 4 Kelvin. Now let's calculate the Z magnetic moment and the susceptibility CZ using Curry, sys, exp. Here I did not specify which outputs I want. Curry by default, if you don't specify anything different, it will always return 2 things: the magnetic moment and the susceptibility, the ZZ component of the susceptibility. Now, in order to plot the results, let's make a subplot 1, 2, 1 and plot the B field. Where is our B field? Exp.field. What we should probably do, we should do it this way. Call this B and assign exp field to B. So we can just use B here for the plotting. B mu Z. And we're going to do another subplot, and we're going to plot chi ZZ. Let's see whether that works. And there you go. We've got on the left-hand side, we've plotted the magnetic moment, which increases as you increase the magnetic field. But as you can see, it starts going flat with increasing field. And that's seen here on the right-hand side, which is the magnetic susceptibility, which is kind of the derivative of the magnetic moment with respect to the field. And it starts off large and it starts dropping. So Curry supports arbitrary spin system. You could have even 5 coupled spins with arbitrary couplings between them, because it's just based on the same machinery as all the other EasySpin functions. It constructs a spin Hamiltonian, sets up the energy level diagram, calculates all the Boltzmann populations, and does the thermodynamic average to get the magnetic moment and the susceptibility calculated. That is a brief overview of Curry. I encourage you to look at the documentation. And reminder, a warning for those who have used Curry before. Curry has changed quite a bit since its initial release. And you will find that it got a little better, it got a little faster, and the interface is cleaner. However, the documentation is not quite up to date yet. So the function reference is good, whereas the user guide, which is here on the left, where is it here? SQUID magnetometry. It still needs some work. It still has partially is reflecting the old version of Curry. But if you're if you just wait a few more weeks, we will have a updated and polished documentation for Curry out. These are all things I wanted to mention for Curry. This is just a quick overview. And so in this session, we looked at Curry for SQUID magnetometry and also on how to interface ORCA with EasySpin to import quantum chemistry calculation results. We'll conclude this session now, and I'll see you again for the next session that starts in about 19 minutes. And in that session, we'll look at more in detail about how to specify broadenings for EPR spectra. And we look at coupled spins, at some effects that you can see, and people often wonder about coupled spins. Until then, see you.